Hey everyone, welcome back. Let's see, last time we were talking about binary structures. That's where we left off. So a binary structure, that is a set S together with a binary operation star, right? And this pair is just a way of collecting the two together. So there's nothing deep going on here. It's just saying a binary structure is a set together with a binary operation. And at the end of the class, I think I said something like this, that in its broadest sense, you can think of abstract algebra as the study of algebraic structures, or sorry, binary structures. So let's look at a couple of examples. And so I'm going to draw the tables corresponding to a couple of binary structures. And I guess I should first write down who the set is. So the set that I want to consider, capital S, all right, that's A, B, C, and D. And I'm going to draw the tables corresponding to two binary structures. So the first one, I'll use the symbol star, all right? So I'm going to write out A, B, C, D, A, B, C, D. Let's get our rows. Get our columns, and then remember, in each of these spots, I'm going to write down the corresponding element. So for example, or let me fill this out here. So A, B, C, D. So the first row, A, B, C, D. So what this means is A star A is equal to A star B equals B, A star C equals C, A star D equals D. And let me fill out the rest of them. B, C, D, A, C, D, A, B, and D, A, B, C. So remember how you interpret this. When I get to a certain spot corresponding to a row and a column, this element right here, so it is C star C. This one right here, this D right here, what we're saying is that C star B equals D, right? So this table right here tells us how the binary operation operates on or behaves with respect to S. I'd like to do another one, and I need to use another symbol now. So now I'll use the symbol dot instead. A, B, C, D. A, B, C, D. Okay, so let me fill this one out. A, B, C, D. B, A, D, C. B, A, D, C. And then C, D, A, B. And D, C, B, A. Okay, so what does this mean? So for example, C dot D is equal to B. All right, so it's always row, then operation, then column. Sorry, I just ate a peanut and now it's stuck in my throat. So I want to just take a look at these. We've got two different binary structures. So let's say something like this. The binary structures and in this case, we've got two of them. One of them is S star. The other one is S dot. And I would like to, I need to finish this sentence here. I'd like to make the argument that these two binary structures are fundamentally different, right? They are not the same. So, let's say it like this. These binary structures do not behave the same. And I guess I need to put this in quotes, because I mean, what do we mean by the same? Well, let's look at just some of the ways that things multiply out. And so, for example, if we look at, so we'll say, for example, A star A star A equals A, and C star C equals A. So we have in this table over here, we've got A star A equals A. We've got C star C equals A, but oops, I need to say, sorry, I need to say a little bit more. So for example, let me just write out what I actually want to do is write what happens to each of the elements when you do the operation applied to itself. So, so let's notice that A star A equals A. B star B equals C. C star C equals A. And D star D equals C. D star D equals C. But, sorry, I'm running out of room here. If I look at what happens when we do dot applied to each of the elements individually, what we get is A dot A equals A. B dot B equals A. C dot C equals A. And D dot D equals A. D dot D equals A. So we have these two different, well, I shouldn't say different until we really convince ourselves that they're different. We have two different symbols, which are binary operations on our set capital S. And here's what we want to notice. Okay, the behavior, when we look at C, that behaves the same, right? C or A star A and A dot A give us the same output. They both give us A. Same with the C's, but then when you look at how B behaves and how D behaves under star versus dot, we get different outputs, right? B star B equals C, but B dot B equals A. Right? So this evidence right here should convince us that somehow these are not the same operation, right? These are two distinct, completely different binary operations. And so now I want to leave this one up, the star one, and I would like to look at another binary structure. So let's define, so I'll say now, and I'm essentially still working within the same example. So now let's define a binary operation. So the binary operation triangle on the set T, which will be the number 0, 1, 2, 3, by the following formula. It's going to be A triangle B is equal to A plus B mod 4. Right, so we've got a new set, the set of integers 0 up through 3, and then we're defining this new operation, and I need to use a different symbol here, so I'm using the symbol triangle. So triangle is the symbol for the binary operation, and here's the formula. So now let's draw the table corresponding to triangle, and now we've got the numbers 0, 1, 2, 3, 0, 1, 2, 3. Okay, so we need to fill out all the entries here. So let's see, 0 triangle 0 is 0, 0 triangle 1 is 1, and then we'll get a 2, then we'll get a 3. The next one will be, it'll go like this, 1, 2, 3, and then 1 triangle 3, that's going to give us 4 mod 4, which is 0. Then we'll get a 2, 3, 0, and 1. and then we'll get a 3, 0, 1, and 2. And now I want to compare these two tables. I know that we've got a set A, B, C, D here. We've got the set 0, 1, 2, 3. But if you notice the behavior of, let's say, I don't know, let's look at this diagonal right here. It goes 0, 2, 0, 2. It goes A, C, A, C. And notice A is the first element in S, while 0 is the first element in T. C is the third element in S, and 2 is the third element in T. So notice it goes first element, third element, first element, third element, first element, third element, first element, third element. And if you did this for each row, so for example, notice how the rows go. First element, second element, third element, fourth element. First element, second element, third element, fourth element. And then let's compare, I mean, you can do this on your own. Let's compare row 3. Second element in both cases. Then, third element in both cases. Then fourth, then first, then second. By comparing row by row, what you should do is convince yourself that these are essentially the same. That the binary operation star on S behaves exactly the same as the binary operation triangle does on T. Right? So by comparing the tables for S comma star and T comma triangle, we see that they are the same. And I'll still put that in quotes. We need to make this sameness precise in the following sense. What we have is this correspondence, right? There's a correspondence that matches A with 0, B with 1, C with 2, and D with 3. Okay, so what? Yes, of course there is. There's 4 elements in both sets, so of course there's a bijection between them. But the correspondence is a little bit stronger. So we need to say, and this is the important part, it's not just the fact that there's a bijection between the set S and T. That's not so exciting. The exciting part, the thing that we want to notice here, is that this correspondence pays attention to, it respects the binary operations. So in the sense where A star A corresponds to 0 triangle 0. And A star B corresponds to 0 triangle 1. Let me write down, I'm not going to write down all, there's 16 different ones to write down. I'm not going to write every single one of them down. What else do we have? Just pick one. C star C corresponds to 2 triangle 2. And I'm going to say etc. here, ... The point is, if you take any two elements, any pair of elements on the left, and look at their star, it will correspond under this arrow to the same choice of the two elements, the corresponding choice of the two elements on the right-hand side, and their triangle operation. Yeah, okay, so now let's try to make this idea more precise. So in general, we should view binary structures S comma star, and what symbol do I want to use? Let's say and T comma dot as indistinguishable if well, okay, so if there's a one-to-one correspondence between the elements, so if there is a one-to-one correspondence, let's just say S, and I'll put a little double-headed arrow here, so one-to-one correspondence between S and T, so that for each, I say X and Y in capital S, there's a correspondence let me say this a little bit better so that if let's do it like this, A and B are in S, and X and Y are in T with A corresponding to X and B corresponding to Y, then A star B corresponds to X dot Y. So the correspondence respects the operation. Okay, so now let's make this truly precise. And we're going to use the word, instead of saying that the binary structures are indistinguishable, there's an actual word, a common algebraic word for this. So now for our definition, binary structures S comma star and T comma dot are isomorphic. Iso means same, morphic or morphism is change, right? So they've been changed, but they remain the same. That's the idea. So isomorphic, if there exists a bijection phi from S to T, that's the one-to-one correspondence that we had down here. Now I'm actually using the symbol phi for that one-to-one correspondence, the bijection, such that for all what I use here, A and B in S, we have phi of A star B is equal to phi of A dot phi B. This is one of the fundamental concepts of all of abstract algebra. We relate the two binary structures via a mapping, a bijection, that respects the two different binary operations. Right? That's called an, or that's when that happens, we say that they're isomorphic. And phi itself, so the mapping phi is an isomorphism. Right? So isomorphism, things have changed, but they're still the same. And so one way to think of an isomorphism or isomorphic binary structures is all we did was we changed the names of the elements. An isomorphism is really just a renaming of the elements of the set but the structure beneath it, the multiplicative structure, and we'll see that this binary operation we can somehow view as multiplication, right? The structure that has been given to the set by the binary operation does not change, even though we've renamed the elements to a new set T, and we're using a different formula. The underlying structure is fundamentally the same. So the example that we did before, so let me just put that down officially. So with S star and T, I was using triangle with S star and T triangle as before. The mapping phi from S to T defined by, and here what do we have? Phi of, what are the elements? A, B, C, and D. Okay, so phi of A equals 0, phi of B equals 1, phi of C equals 2, and phi of D equals 3 is an isomorphism. And when we have an isomorphism, what we said then is that the two binary structures are isomorphic. The material that we just finished here, right, finishing off with this idea or this example of an isomorphism and our discussion of binary structures, that I kind of blended the first 3 chapters. So it would be chapters, let's see, in your book, I guess it calls it sections. They're called sections in your book. But so they would be sections 1, 2, and 3. I somewhat blended those together into the first lecture and the second lecture. From here on out, right, and I didn't label those. From here on out, I'm going to label my chapters, and my chapters will correspond to the book chapters. So that if you want to follow along and you'll see how the book corresponds to the lectures, you'll see that they match. Now, one thing to be aware of, I'm going to label my theorems. My theorem labeling will not necessarily match the labeling of the book. So the chapters will match, but the labeling of the theorems may or may not match. Occasionally, I will have an additional theorem that's not in your book. I will sometimes skip some of the other theorems, and so or I may reword them, break them up differently. So chapters will match, theorem numbering will not. Okay?